Hello, this chemistry video has to do with empirical formulas and how to derive the empirical formulas of a, say, compound based upon some chemical experiments we might do or analyses we might do of it. I am following Brown, Bursten, LeMay, and Murphy's textbook, Chemistry, the Central Science. We're in chapter 3 of that textbook, which is on stoichiometry, and in particular, how to make calculations with chemical formulas and equations. So this particular video is on empirical formulas. Again, we've seen empirical formulas before, earlier in this very same chapter, I believe. An empirical formula gives you the relative number of atoms of each element in a substance. It's not the actual formula that you would find in the world. It is rather a simplified version that gives you the ratios between the different kinds of elements. This will make it clear if that didn't make sense in the abstract. So take glucose, simple sugar. Its actual molecular formula is C6H12O6, so for each unit of glucose, you have 6 carbons, 12 hydrogens, and 6 oxygens. That's the molecular formula, the actual real-world formula. Now, the empirical formula gives you the ratios, the simplified ratios of these elements in proportion to each other. So you can see that 6 is the common denominator. If we divide each by 6, we get CH2O. This is not the actual formula of glucose, but it is an empirical formula that gives you the ratios of the elements. So for every carbon in glucose, there are 2 hydrogens and 1 oxygen. These are the ratios of the elements. So we can actually go from experiment to the empirical formula to the molecular formula. By the way, it also gives the ratios of the moles of each element. So for every mole of carbon in glucose, there are 2 moles of hydrogen and 1 mole of oxygen. Well, it may become clearer why this is useful if we start with an example. So let's say we are given a sample that has 5.325 grams of methyl benzoate. Now, let's say I don't know anything about methyl benzoate. I've never methyl benzoate in my whole life. I don't know what that is. Well, I just know, somebody tells me, well, I think it has some carbon, and it has some hydrogen, and it has some oxygen. So what's the formula of this thing? Or the first step, let's say, what is the empirical formula of this thing? Well, let's say we do some analysis, and we find out that in every 5.325 grams of methyl benzoate, there is 3.758 grams of carbon, 0.316 grams of hydrogen, and 1.251 grams of oxygen. Okay, now we're talking business. So what we can do is we can find out how many moles of carbon, how many moles of hydrogen, how many moles of oxygen there are in this particular sample. So let's go for it. So let's start with the carbon. We know that the atomic number of carbon is 12 grams per mole. You can flip it and say there is 1 mole of carbon for every 12 grams of carbon. So if we have 3.758 grams and we multiply it by this, the grams are going to cancel out and we'll be left with moles. We end up with 0.313 moles of carbon. Okay, so tuck that away. We have 0.316 grams of hydrogen. So 0.316 grams of hydrogen, we know there's the atomic number of hydrogen is 1 gram per mole. So 1 gram per mole. Flip it, doesn't matter, it's all 1. And we end up that we have 0.316 moles of hydrogen. Now these aren't exactly the same mathematically, but we can suspect they're close enough to each other that there's a 1-to-1 relationship between the number of carbons and the number of hydrogens in this thing. And there's just a little experimental error that has crept into our formula here. Finally, we have 1.25 grams of oxygen. We know the atomic number of oxygen is 16. Flip it good. Grams will cancel out and we'll be left with that divided by 16, 0.078 moles of oxygen. Now, what is the ratio of these to each other? We know this is 1-to-1. We're going to have to do a little math here. I'm guessing 4. So what's the ratios? We have 0.313 moles of that, 0.316 moles of that, and 0.078 moles of that. So what the ratio is, if this is the 1, so how many of these are there for every, we take the lowest number, actually you divide by the lowest number, this by the lowest number, this by the lowest number, and this by itself. And so we find that this is, if this is the 1, then this is going to be, these are, as I said, these are both 4 times this. So we know that the empirical formula for methyl benzoate, is that what it was? Methyl benzoate? Yes, methyl benzoate is going to be 4 carbons for every 4 hydrogens for every 1 oxygen. That's the empirical formula. It's not the real molecular formula. We're going to find out about how to get to that next. But it is the relationship of the proportions between the various molecules in one of methyl benzoate. Okay, so part 2, the molecular formula. How do we get from the empirical formula, which is the proportions, to the molecular formula, which is the actual formula in which a substance occurs in the world? Not just the ratios, but the real world number of them. So we're going to use the molecular weight in grams per mole to find it out. So the subscripts in the molecular formula of a substance are going to be a whole number multiple of the subscripts in the empirical formula. What are you saying? What are you saying? What I'm saying is that if this is the empirical formula for methyl benzoate, then the actual molecular formula is going to be some multiple of this. So it could be C8H8O2. You multiply everything by 2, or we can multiply by 3. C12H12O3, multiply it by 3. It turns out that the actual molecular formula of this is twice C8H8O2. And so the actual formula, the molecular formula, is going to be some multiple of the empirical formula. Okay, let's look. Our example here. So we're dealing with ethylene glycol. And let's say that we find out experimentally or somehow that for every 1 bit of ethylene glycol, it is 38.7% carbon, 9.7% hydrogen, and 51.6% oxygen. Okay, so let's figure it out. We know that, so let's imagine that we have 100 grams of this. So in 100 grams of this, we would have 38.7 grams of carbon. Well, I've gone ahead and instead of multiplying by the inverse, I've just divided by 12. It's the same thing, right? Grams divided by grams per mole ends up moles. I could have done it the way I did it on the previous one, where I wrote all this out, but you can see that it's basically the same as dividing by. To save space, I've just done it in this way. So if I divide this by this, I get 3.2 moles of carbon in 100 grams of ethylene glycol. I can then take the 9.7%, and if I had 100 grams of ethylene glycol, then 9.7 grams would be of hydrogen. Times 1 gram per mole equals 9.7 moles of hydrogen in 100 grams of ethylene glycol. Lastly, I'm going to take the 51.6%. If I had 100 grams of ethylene glycol, then I would have 51.6 grams of oxygen divided by 16 grams per mole, which is the atomic number of oxygen, and I would have 3.3 moles of oxygen. Notice again, these are the little experimental error, but we can basically say that for every 1 carbon in the empirical formula, there's going to be 1 oxygen. What about this? Well, this looks like being about 3 times it. So the ratio is 1 carbon for every 3 hydrogens for every 1. And so the empirical formula is CH3O. That's the empirical formula of ethylene glycol. That's what we did in the first part of this video. Now, how do we get to the molecular formula? Well, we are told in the problem, and I'm doing one of the examples here that wasn't solved. They told you the answer, but they didn't actually play it out. I'm doing the work here for you. The molecular weight, let's say, of ethylene glycol is 62.1 grams per mole. Okay, so basically, if the empirical weight, so let's say the atomic number of C is 12, they've got 3 hydrogens, we've got 16, so add that up, 31. So the empirical weight of the empirical formula is 31. How many times does 31 go into 62? Looks like 2 times. And so if I multiply this by 2, I get C2H6O2. Voila! This is the molecular formula for ethylene glycol. Okay, so this is how you first how you get the empirical formula, and then how, if you have the molecular weight, you can then figure out what the actual molecular formula is. Okay, one more section in this section, a subsection, and this is combustion analysis. We've been doing a lot with carbons and hydrogens and so forth. So one way to determine the empirical formula of especially something that's carbon-hydrogen type stuff, gas, is by burning it. And so when you combust these sorts of molecules, you get CO2 and water. The carbon goes into CO2 and the hydrogen goes into H2O. And so you can actually figure out what the amounts of C and H were in the original thing you burned up. And that can lead you toward figuring out what the empirical and molecular formulas of something are. If there's a third element, you can find by just subtracting what you know of the carbon and hydrogen from the original compound. Now, what does that all mean? Well, let's do an example and find out. So, caproic acid, apparently this is what makes socks smell. My socks sometimes smell. And so it gives me great joy to know what it is that's smelling. It's caproic acid. So let's say that we have 0.225 grams of caproic acid, okay, and we burn it, and it yields 0.512 grams of carbon dioxide and 0.209 grams of water. Okay, so it has absorbed some oxygen from the combusting, so we're going to ignore the oxygen in these two. So let's start with the carbon dioxide. So we know that we have a result of 0.512 grams of carbon dioxide. Now, what is the molecular weight of carbon dioxide? Well, we have a 12 and 2 16s, so 32 plus 12 is 44. Okay, 44 grams per mole is the molecular weight of carbon dioxide. So if we divide grams by grams per mole, we get moles. And so we know that we have 0.0116 moles of carbon dioxide, and I've been careful. First couple times I wrote this down, it came out wrong because I didn't do significant sig figs. There are 3 significant figures here, so I'm going to do 3 significant figures here too. So I know that I have that many moles of carbon dioxide as a result. That means since there's 1 carbon for every 1 carbon dioxide, I know that I have 0.0116 moles of carbon. And since matter cannot be destroyed, I know that there must have been 0.0116 moles of carbon before the combustion as well. What about the hydrogen? Well, if I take the 0.209 grams of hydrogen and of course of water, that is. Now the molecular weight of water, 16 plus 2 is 18. Okay, grams divided by grams per mole cancels out and get moles. And so basically when I do that, I find out I have, oh look, 0.0116 moles of water. So however, in 1 mole of water, there are 2 moles of hydrogens. So I've got to double it, 0.0232 of hydrogen. Okay, so now I know how many moles of hydrogen I had to start with, because I know how many I ended up with, and I know how many moles of carbon I had to start with because I know how much I ended up with. Now I'm going to do a little subtraction. Well, no, I'm not. I'm going to figure out how many grams I started off with of carbon and hydrogen. So this many moles of carbon times 12 grams per mole plus this many moles of hydrogen times this many grams per mole. Basically, I would have had 0.162 grams of carbon and hydrogen to start off with. So now I need to know the third component, which is oxygen. I was told that we began with 0.225 grams of caproic acid. And I know that of that 0.22 grams, 5 grams, that 0.162 grams of it was hydrogen and carbon. So if I subtract that out, I know that I must have started with 0.063 grams of oxygen, right? So now I've got this number of grams of oxygen divided by 16 grams per mole of oxygen. I know that I had 0.0039 moles of oxygen to start off with. So I know I had 0.0116 moles. Actually, I think I put it on the next It's a ratio of 3:6:1. So for every 1 mole of oxygen that I had 3 moles of carbon, and I had 6 moles of hydrogen. So it's just multiples. This is the lowest one. So I know for every 1 mole of this, I had 116 divided by 39 is 3. And then this is 6. So this is the empirical formula, 3:6:1. All right. You can ask questions, although you can put them in YouTube comments if you have questions, but hopefully that makes some sense. So I know the empirical formula, C3H6O, empirical formula. Now, so if I add up the baseline mass of that, 3 carbons is 12 times 3, 36, 6 hydrogens and 1 oxygen. So 59 grams is my base empirical weight, as it were. Now, I'm told that the molar mass of caproic acid is 116 grams per mole. So how many times does this go into this? 2 times. And so I'm going to take my empirical formula, multiply it by 2, and that'll give me the molecular formula, which is C6H12O2. All right, well, I'm sure I could have said that more clearly, but I have tried my best to give you 3 examples for the 3 subsections: empirical formula, then going from empirical formula to molecular formula, and then using combustion analysis to try to get at the empirical and molecular formula. All right, there we go. Empirical formulas by analysis.